Yeah.
Where?
Yeah.
Okay, good. Thanks. Okay, I'm supposed to give you a report on what this second International Linear Collider Technical Review Committee is doing. And from the very many questions that I got in the last few months about this, I know that there's a tremendous spectrum of expectations of what we're going to produce and what our conclusions are going to say. And at one end of the spectrum, there are the people who believe that the final paragraph of this report is going to say, this is the machine you pick, and it's going to be very clear and unambiguous. And then at the other end of the spectrum, there are people who have told me, please do anything you want, but don't make comparisons. And so in between, there are a lot of different possibilities. And some of this confusion came out because when ICFA asked us to do the study, the charge was very, very long. It was about 3 pages long, and it was written by 3 different people with slightly different opinions. So what I've done with the committee in the last few weeks is I've rewritten the charge. I've made it much shorter, and hopefully it's not as ambiguous. And so here is what we wrote and what we more or less agreed to. So the second committee is to assess the present technical status of the 4 linear collider designs at hand and their potentials for meeting the advertised parameters, the parameters that they advertise at 500 GeV center of mass, use common criteria, definitions, computer codes for all these assessments. Or try at least, it's not always possible. Second, to establish for each design the R&D work that remains to be done in the next years to prepare a conceptual design report from which you will know what the machine looks like, but also from which you will be able to compute a hopefully reliable final cost so that construction can be based on a believable cost. Then to assess the potential of each design for reaching higher energies above 500 GeV. Every word here it means something. We said above 500 GeV, we didn't say what, because there are discrepancies between what the potentials of the various machines are and what work is needed for that. And then finally, they asked us to look at whether there are other possibilities, other areas of collaboration, and that's very natural. That's working pretty much by itself. Okay, just to give you a little background for 2 or 3 minutes about what we did the first time, because that also taught us what to do and what not to do the second time. The first time, the whole story started pretty much in 1993 when there was a meeting at SLAC, the LC-93 meeting, at which Daisy, KEK, and SLAC agreed to write some informal MOUs to organize an international collaboration and to create a collaboration council. And in July of 1994, at the EPAC meeting in London, this collaboration council, which was led by Dave Burke, by the way, and was totally ad hoc. It was not didn't come from ICFA or anything like that. Got together, and they asked us to do this study. So around 1994, in the fall, we got organized, and about a year later, we published the first report. The charge was not too different from the charge I reconstructed now. Basically, it was to compare the machines. There were a very large number of machines, as you'll see in a minute, many more than we have now. And we were starting from basically 0, because everybody was using different parameters, and we couldn't really compare apples and oranges. The first job was to put everything on equal standing. And then to look at the same thing again, the energy and how the luminosity increases with time and so on. Anyway, a year later, we put out this report. Like with everything you do in this field, international collaboration, there are always hassles. One of the worst hassles happened the last day before, or 2 days before we were going to publish this. We noticed at the last minute that when we put the map on there, we thought it was a great thing to have a map. Hawaii dropped out for some reason, and it was important because people were thinking of building the machine in Hawaii at the time. Corsica never got on the map, and the map of Japan was totally distorted. So we were going to have an international crisis, but it was avoided by getting a better copy. But that tells you that this is not an easy job. There are a lot of... Okay, now, the structure that we used at the time was based on the idea that to keep everybody honest, we would bunch people together by expertise. So there were all these groups, and that was good in a way for the first time because it meant that people that knew things about the same thing got together and they kept each other honest. So there was a group on injections systems and pre-accelerators. There was a group on damping and compression systems. There was a group on Linac technology. There was a group on beam dynamics, group on beam delivery, and a group on experimentation, which was led by Ron. Oh, he disappeared. No, there he is. Anyway, the good thing about this was that everybody really was able to compare what they were doing. The bad thing was that when we were all done, there wasn't any vertical integration except through the beam dynamics group, but nobody was able at that point, we didn't have the time, to go from the first point to the end and see whether the machine was going to really work as a whole. But in a way, it was premature because the R&D was at its beginning. And when I said that there were many machines, here was the mega table that summarized everything about the beam. There were, at the time, there was Tesla, but in Germany there was an equally aggressive effort to come up with an S-band machine. There was a JLC-S, the JLC-C, the JLC-X, the NLC-X. The Russians had a project called VLEP at 14 gigahertz, and then click. Now, as you know, at least 3 of these projects have disappeared from the map, which makes things a lot easier. But at that time, we had to get everybody together. There were about 50 people on my committee, so it was a long affair. Okay, now let's talk about what we're doing now. About a year ago in February, ICFA got together. Now this time it was ICFA, it was not the Burke Committee. And they discussed this matter. And the conclusion of the meeting was to request a second study. So I got a call from first Jonathan, then Sugawara, and then Wagner, and they all asked me to do this, and I finally succumbed, okay? And I agreed to do it. And it took a few months before we could agree on how to put this together. They had some very specific questions about how we would, what kind of committees we would have, or at least what the steering committee would do, and so on. And finally, we submitted a proposal at the ICFA meeting in Rome, and it was accepted. So then the working groups were put together. And I'll tell you about the working groups a little later, because that's crucial to the whole thing. In November of last year, the working group started. And then recently, just before Christmas, we got these mega tables almost completed. So at least we have something which has on 6 pages the details, almost all the details of all the machines. Okay, on the committees, I have 4 people in the steering committee, and their jobs are much more than steering, actually. There's Reinhard Brickman, who was here from DAISY, Karo Yokoya from KEK, Tor Robbenheimer from SLAC, and Gilbert Guignard from CERN. Now, their job is not just to steer this operation. Their job is to write 4 major chapters, as you'll see, which will describe their machines. They are the people responsible for having in this book a complete description in about 30 pages each of these machines. Each of them will be in there. And then the 4 machines, of course, the survivors are, as you well know, Tesla, JLC-C, which is a small effort, which is actually in many ways grafted onto the JLC-X for most of the peripheral systems like the damping rings and so on, the injectors, but has a fairly advanced bunch of prototypes for what is needed to build this machine at C-band. Then there is the JLC-X, NLC-X, which is now one project. There are very, very minor differences. They're trivial. They have to do with the electricity rep rate in Japan versus the US, 50 cycles versus 60 cycles, things like that. Very, very minor. And then, of course, there's click. We have now a table of contents of what we will hopefully have when we're done. It has the charge, the plans, the membership of the committee, the mega tables, which will summarize everything, the 4 machine descriptions that I just discussed, the upgrade to higher energies, description. Number 5 is probably one of the most important things. Description of the R&D that still remains to be done on all these 4 machines. What is going to be done, how it's going to be done, and when. When is probably the most important, because as you just heard from the previous speaker, if we want to build this thing, start building this thing in 5 years from now, we can't go on forever. Okay, we can't continue to modify these designs and do R&D forever. Then there will be a description of the and goals of the test facilities. That would be pretty much like what Kubo-san described today. And then the working groups. Now the working groups, instead of doing what we did last time, we decided to have vertical groups which map into what Steve was talking about, namely the 2 most important things about this machine. 1, can you reach the energy? And 2, can you give the luminosity that you promised? So we divided the working structure into 2 groups. One is this one, and the other one is this one. Then everybody is telling us, and you heard this already, that there hasn't been done much about reliability. It's very difficult because there are always tremendous surprises. Even if we had an incredibly detailed reliability study on SLC, I think we would have been totally surprised, because most of the things that people thought were going to work, some of them didn't work. We had tremendous anxieties about the energy. The energy was reached easily. We thought the arcs, some people thought the arcs were going to work fine. They were a disaster. The amping rings were completely different from what we thought. So whatever you do in this reliability, you can't be sure. But at least we have to do more than we have done. We haven't done very much. Okay, so as of now, as I said, we have the first tables ready. There are a few X's there where we don't know what the numbers are. And what we're doing this time is we're putting the energy range, or the 2 energy goals, on the same table. So there's, for example, Tesla 500 GeV, Tesla 800 GeV, JLC 500 GeV, JLC 1 TeV, same thing for JLC NLC. And then for Click, obviously there's a much bigger range, because originally they were working on 3 TeV, and now they've come down to 500 GeV to be competitive, or to start, or to propose something earlier than they thought. And then all these parameters which you have heard about and I won't go into. And we have this, as I say, we have 6 of these tables. Now, I want to say a little bit about the working groups. The working groups, it was quite an exercise to get the membership of the working groups geographically fair, expertise fair, lab fair, and so on. So finally, this technology, RF power and energy performance group, we found a chair for this group, Daniel Boussard. He had just retired from CERN and thought he was going to have a long, long vacation where he lives on the French Riviera in Provence, but we interrupted this, not vacation, this retirement, and he's now agreed to do this for the next 9 months or so, which is very nice because he doesn't have any other commitments. And then we have these various people in the working group: Chris Adolphson from SLAC, Helen Edwards, Kurt Hubner from CERN, Hans Weiser from DAISY, Mark Ross from SLAC, Nobutogi from, you probably know a lot of these people, maybe not all of them, Shintake from KK, he's the guy who's doing the C-band, Ralph Pasquinelli from Fermilab, Lilia from DAISY, Perry Wilson from SLAC, I have one fellow from BINP in Russia, and Hans Braun from CERN. And what they are doing is, what you can guess, everything that has to do with the technology and the ability of the designs to actually get to the energy, whatever the energy is, 500 GeV or whatever. And, of course, also this question that came up today, which is to change the energy, to change it fairly rapidly, and to see how we do this, whether it's by quanta or you can go to any energy and how fast you can do this. And so that was added as an assignment recently because everybody knows how important it is. Okay, the things that they worry about are the things that you heard from Steve already. Worry about structures, power sources, power distribution, injectors, beam delivery, and the reliability in all these systems. And they have started. They're all actively engaged now. But, of course, I have to say that every single one of these people is working, except for Bussard, is working on a machine, his own machine or her own machine, and is very busy. They do this as volunteers, and it's hard. It's hard to get them to do things, but they're really good citizens. I have to say that. Now the Luminosity Performance Group. Here again we lucked out in a way, because Jerry Dugan from Cornell agreed to do this, and Jerry just happened to be another case of somebody who was going to take some time off. He was going to go to LBL on a sabbatical, which he is doing, but instead of doing what he was planning to do, he's doing this. So, so that's good, because we have a lot of his time, and he's taken this on with a vengeance. Okay, who are the people of this group? Is Ralph Assmann from CERN, Peter Tenenbaum from SLAC, Jacques Garrett from CERN, Kozanetsky from Saclay, he also spent some time at SLAC, Nan Finney from SLAC, Daniel Schulte from CERN, Nick Walker from DAISY, Andy Volsky is an expert on the damping rings and LBL, Ron Settles sitting right here, Joe Rogers, Andre Seri, and Winfried Decking. He's also a damping ring expert. He's the one who's worrying about the dog bone. And so what are these people doing? Well, it's kind of obvious what they have to do. They have to go through the systems, but they have to go vertically, so all the systems from A to Z, not like we did the first time. So they're looking at the sources, the photocathode and conventional, this is electron sources, positron sources, polarization, production, preservation, damping rings, you already heard the problem, emittance in, emittance out, the big problem, whether we're going to make that, polarization coming out of the damping rings, beam transport from the damping ring and the bunch compressors all the way through the main Linux, beam delivery, the beam effect at the IP, and then the dumps. Collimators, background. These are, by the way, these are little subgroups that have mixed the people in the big group into these activities, but they're all reporting to Dugan, and he's coordinating all of this. And then finally, the question of reliability, operability, luminosity, and percent of the energy spectrum, and so on. Okay, so they're well launched. The milestones now in the time in this year that we have are sometime by the end of this January, we hope to have the chapters of the descriptions finished of the 4 machines. And then in February, as you heard, we have this big ILC-02 meeting at SLAC, at which all of these people, plus many others, there are over 120 or 150 people coming to this, are going to be there as sources of information, and the members of our committee are going to be there, and we're going to have a day and a half at the end to begin to see how we put all of this together. Then hopefully in April, somewhere, location to be determined, we'll have another meeting of this group. And then, this is the most scary word here, first draft. I don't know what that draft will be, but anyway, we've been asked to give some kind of a report at the EPAC meeting in June in Paris. And then there's the final drop dead date of October to have the report ready. So that's our plan now. You heard about this ILC-02, and this is the structure of this meeting, which is not directly related to what I'm doing, but has all these resources and all these people. It's going to be a great help to have all these people in one place for a week at SLAC. Okay, to end my talk, I just want to say what I think might come out of this at the end. I'm very encouraged, as I said before, that I've seen how these people work together. It's not easy because we do it by telephone, we do it by email, and by video conferences. Sometimes it's almost impossible to set up a conference that has a coincidence of somebody in Europe in Palo Alto and in Japan at the same time, because either one is sleeping or just waking up. But we've already failed once to do this, and we succeeded, and Jerry's group succeeded another time. So these people are really, the best thing I can say about what might come out of this is that the process is perhaps more important than the product. The process is getting people together, they're working together, they're talking, there are not too many egos involved, there probably are, but they are really trying to do a good job, and they're comparing what they're doing with others, and they're helping each other, which is not just competition, but it's also maybe an omen that when a decision is finally made that we're building one machine, that people won't fight, that they will have known each other well enough, they will know how to work together, they will accept the fact that we can only build one machine in the world, and we'll try to build the best one. And this was very comforting to me to listen to the discussion last time. It was just great to see how these people are arguing with each other. You hardly know anymore when you hear them argue who is representing what. Okay, so I think that's going to be achieved for sure. There's also hopefully going to be an agreement, as you heard from Steve, but hopefully an international agreement of what everybody has to do, when and how, to get this 500 GeV design to be reliable. We're not there yet, as you heard. There are a lot of loose ends, and we'll have to agree in some way that these things have to be done. If we don't, then you can't even talk about comparisons, because somebody will be in one stage, somebody else will be in another stage. So we have to have this agreement, and I think this will come out of it. I think we'll also, hopefully, get some criteria, generalized criteria for site selection for either one of these machines. We won't, of course, we won't get into the idea of selecting the site, but we will have the criteria. We will have, hopefully, as similarly to 2, we will have a roadmap of how the CRDs, if each machine has a CRD, or at least 2 of them have a CRD, that the CRD will be written in a way that will be believable, and that they will supply a foundation to determine the cost. And then, of course, the last point is the most difficult one. The 5th point is the fact that maybe, I don't know. I mean, this is impossible to know. Maybe there will be some very strong recommendations coming out. Depends on how things look. But you have to realize that they have to come out by the fall. And you've also heard all the loose ends that are still to be worked on. And there will be some preferences. But these preferences for one machine or the other, they will be tainted. And you have a responsibility in this, because the energy reach is important. And if we knew for sure that you wanted a certain energy, or that we had to reach a certain energy, then that might taint the decision. We also are very much tainted by what was said by several speakers this morning, and that is that if we're talking about a machine that's going to cost $5 or $6 or $7 billion, you cannot do this by starting at 16 or 18 or 19 million dollars per year. We have to increase. We have to talk to the people who give us the money. We have to convince them that we will not have a believable study, not just this study, but everything else we're doing here, if we just work with this very small amount and ridiculous amount of money. We can't do it. It has 2 repercussions. The one repercussion is that you don't have enough money to do the work, and the other thing is it stretches everything out. So this 5 years, who knows what this 5 years is? It could be much longer. It could be much worse. Okay, and we don't want to wait forever. And then, of course, there are confidence levels and risks. And finally, there's the politics. As you remember, Henry Kissinger always explained everything by saying, you have to study the geopolitics. Well, there is going to be geopolitics in this affair. I mean, it's not going to be completely independent of what the various countries can do, want to do, what budget deficits we have, what budget surpluses we have, and so on. So obviously, there are some things that are not in our hands. But that's all I can say right now. Thank you.
Thank you very much, Greg. We have a few minutes for comments. Yes.
Greg, is everybody on the same page with respect to the initial energy The 500 GeV?
Oh, yeah. Yes. Well, there are people who think that you could do with less, but everybody agrees that the study is for 500 GeV, yes. The people in Japan who have said all along that 350 would be fine, but they have agreed to join the study at 500, so that's clear. The thing that's not clear is up, not down.
Greg, I was wondering to what extent you think your committee could handle off-diagonal cross-terms in these studies or in these comparisons. For example, the X-band people found breakdowns in their structures. When they looked at the S-band from SLAC, there were breakdowns, but they hadn't bothered the S-band. So the question is, does the C-band structures break down in the same way, or are they less sensitive? So would your committee suggest, for example, R&D on breakdown studies for C-band?
Yeah, it would be very nice to be able to suggest that, but the C-band project is not funded very well anymore. And sure, the point will be somewhere in between S-band and X-band. But they don't have what it takes right now to do a real study at C-band. They might, but I kind of doubt it right now. The one advantage they have is that they've been asked by Spring 8 to build a free electron laser at C-band, and so in a way they will test their structures and so on. But they won't have the constraints of the very high gradients. But sure, we're learning from each other all the time. In the beam dynamics field, in the ground stability, and in almost everything, there's a tremendous cross-fertilization. And because these people work together, that is happening more and more. So that's definitely happening.
Greg, will your panel address the question of the construction schedule? I mean, we heard from Steve Holmes that, you know, the hope is to be able to turn out RF structures at 1 a month by the end of the year. Now, they actually need to go at like 200 a month to really build that machine on a timely schedule.
No, I don't. No, there are two things that we're not doing. We're not doing industrialization. We don't have the time in the time we have. And we're not doing cost because we were specifically asked not to touch the cost. So we're not doing that. As a matter of fact, in my first transparency, when I talked about the charge here, I said that eventually we have, in this point 4, I said we have to have reliable design so we can find a reliable, establish the cost on a reliable design. And I got a comment from Daisy saying, but are you saying that our cost is not reliable? And I said, no, it's reliable, but it's only an initial cost. It's not based on a final design. And industrialization, as you know, will have an enormous impact on this. As a matter of fact, you know that the Daisy cost did not include any contingency, and the argument was given that the companies that bid on the Tesla machine were not competing with each other, and therefore gave a cost that was too high. And the expectation is that when they begin to compete with each other, the cost will come down, and that will be the contingency. Well, who knows?
When you evaluate those 4 machines, do you evaluate Click on the same footing as Tesla and NLC for a machine which could be built starting in 2006?
Do we do what was Click? I don't understand. What do we?
Do you evaluate the Click machine on the same footing as the others?
We will, but clearly, you notice that Kubo-san today did not talk about Click in the test facilities. They have a test facility. That test facility is going to be ready much later. And so, obviously, the comparisons that we make with Click are based on guesses. One of the biggest guesses for Click that I have to mention, that everybody knows that, is that if there is a physical limitation on gradient that keeps you from going above 80 megavolts per meter, something like that, the Click design is based on 150 or 200, cannot proceed in the way it is constructed right now. So how do we know? We don't know that. So obviously the answer is not clear.
I would like to say something.
Greg?
Yeah.
Sorry, just in 1 minute.
Excuse me, I just want to make one statement to support what Greg was saying about Click. I mean, you have to realize the global situation. First of all, we don't know where the Click is going to work. And they won't know that until CTF3 is done. CTF3 is scheduled to be producing results by 2007.
Now, with these financial difficulties in CERN, that could even take longer. So they can't write what was called in SLAC the ZDR, or what was called in DAISY the CDR, this first design report, until they've done that. So they're 10 years behind NLC and Tesla. So, I mean, they're not really competitors for the low-energy machine.
Therefore, I'm surprised that it's included.
But they've always been in all of
They've been in the club, and they still exist. We took out the people who don't exist anymore. Not the people, the machines.
Can we proceed to the next question?
Greg, over the last months at least, there have been discussions that of these various designs, then each will have its good points, each will have its weaker points, and maybe your report will point to which is the weaker and which is the stronger in these different aspects. However, I imagine that everybody says that we only build one machine, which means that maybe there is a process in which one combines the good with the good and comes up with a single design. Do you have any sense of how that might go or how long it might take?
Well, you can't make it hot and cold at the same time. That you can't do. You can certainly... no, I think that if it's a choice between X-band and Tesla, that eventually, if those are the only survivors, eventually you just have to make a clear choice. And whether we can come up with something by October of this year, I doubt it, because of the reason that everybody's heard here, that there's so many things to do. There are uncertainties. You could probably say that you could build a Tesla LINAC, the LINAC, I'm talking about the LINAC now, at 23 megavolts per meter in a reasonably short time. But then, do they want to do this? It's not clear. You probably want to build a machine that you don't have to rip out completely, so you have to get this 38 megavolts per meter or 35 megavolts per meter in the bag. You have to have that. You have to be able to build it, even if you don't run at that energy. That's, as you heard, is 3 years from now. The SLAC RF business is also 2 or 3 years. So the difficulty of, I was, originally when they asked me to do this study, they said, we give you 3 months. I said, this is impossible. It's ridiculous. You can't do anything in 3 months. 6 months, you can't do anything either. But at least you can study the problems and you can get people together. And as I said, I think the process that we are in is the most important thing, because maybe what will happen is that, well, obviously, if we ever build a linear collider, it'll be one of them, okay? It might adopt some of the advantages in the IP, for example, and the beam delivery. You can do things in common, and the injectors maybe also. But the fact that this whole crowd is working together will make it easier for them to stay together afterwards, whichever choice is made. Mike?
Yeah, I just wanted to ask about the coupling of light sources and other things into the overall facility designs. I'm sure your committee is not going to get into that.
No.
But it somehow is coupled.
It is and it isn't. We decided not to couple it because the only one that's doing that is DAISY. And even at DAISY, there are rumors that they're trying to decouple themselves from Tesla and build a separate laser, free electron laser. And at SLAC, we can't really couple it because we're already building one with the existing machine, which will achieve basically 1 angstrom, hopefully, and it's going to be way ahead of that. So the coupling isn't going to be that good. Politically, it depends. I've had discussions with people that people have the opposite opinion. I don't know. I mean, I can't tell.
Okay, let's thanks Greg Loew again. And out of this meeting, Charles Balté about the working group structure.